Hey everyone, and welcome to Lecture 4 of Real Analysis 2. Today we're going to talk about limit points, but not in the context of limit points of a sequence. Instead, today we're going to be talking about limit points of a non-empty set of real numbers S. So S is just any non-empty set of real numbers. And given a non-empty set of real numbers S, a point P is a limit point of S exactly when, for each epsilon greater than 0, the interval P minus epsilon, P plus epsilon contains a point of S other than P. So every interval of this form is going to contain at least one element of S other than P itself. Now, P may be an element of S or P may not be an element of S. But in order for P to be a limit point of this set S, every interval of the form P minus epsilon, P plus epsilon, for all positive values of epsilon, all intervals of this form have to contain a point of S other than P itself. Now, let's look at a few examples, okay? Okay, our first example. Consider S, where S is the set of real numbers in the interval from 0 to 1. So all of the real numbers from 0 to 1, not including 0 and 1 themselves, that's the set S. And I claim that P1 equals 0 is a limit point of S. Now, why do I say that? Given any epsilon greater than 0, the interval 0 minus epsilon, 0 plus epsilon contains a point of S other than P1 equals 0. And let's just draw a few examples. Let's say that epsilon is really big. So here's 0 plus epsilon. And way over here, off the screen, is 0 minus epsilon. So I have an open interval centered right here. And I'll shrink this down so we can get the whole thing on the screen. 0, 1. And over here we have 0 plus epsilon. And over here, 0 minus epsilon. You know what? Maybe this is a better picture and I don't need the original. So here's the set S, the set of real numbers between 0 and 1. And this is 0 plus epsilon. No. Here's 0 minus epsilon, here's 0 plus epsilon, and this is the set S. Now, does the interval from 0 minus epsilon to 0 plus epsilon contain a point of S other than P1 equals 0? Sure. Here's one right here. 1/2. This is in the interval from 0 to 0 plus epsilon and from 0 to 0 minus epsilon. 1/2 is an element of S, and the interval from 0 minus epsilon to 0 plus epsilon contains 1/2. It contains 2/3. It contains 1/3. It contains 1/4. So this interval from 0 minus epsilon to 0 plus epsilon contains infinitely many points of S other than P1 equals 0. As a matter of fact, this interval from 0 minus epsilon to 0 plus epsilon contains the entire set itself, doesn't it? It contains the entire set S itself. All of these real numbers in this interval from 0 to 1 are contained in the interval from 0 minus epsilon to 0 plus epsilon. So, does the interval from 0 minus epsilon to 0 plus epsilon contain an element of S other than P1 itself? Sure does. It contains all the elements of S. Now let's look at a similar example. You know what? Before we look at another example, let's consider P1 equals 0 some more. We found out what happens when epsilon is very big, but what about if epsilon is very small? So here's the interval from 0 to 1, and P1 equals 0 is our limit point. Suppose epsilon is really small. Maybe epsilon is just this distance. So here's P0 plus epsilon, and here's 0 minus epsilon. And right here is P1 equals 0. Now, does this interval from 0 minus epsilon to 0 plus epsilon contain a point of S other than P1 itself? Well, sure. What about this one? Zero plus epsilon over 2. That's a point in S, right? And it's in this interval. Or what about this point? Zero plus epsilon over 3. And here, 0 plus epsilon over 4. So if we let epsilon be something really small, every open interval about P1 equals 0, from 0 minus epsilon to 0 plus epsilon, contains a point of S other than P1 equals 0 itself. Okay, let's now go on to that next example. Okay, I have the same set S, S is the set of real numbers in the interval from 0 to 1. And this time we'll let P2, our limit point, be the right end point of this interval. And I say again, P2 equal 1 is a limit point of S. And the reason is, given any positive epsilon greater than 0, the interval 1 minus epsilon, 1 plus epsilon contains a point of S other than P2 equals 1. And we'll draw the same kind of example that we did last time. Here's 0, here's 1. And now P2 equals 1 is our candidate for limit point. And suppose we have a really big value of epsilon. Let's say epsilon bigger than 1. For a really big value of epsilon, the interval 1 minus epsilon, 1 plus epsilon, actually contains the entire set S. Remember, S is the set of real numbers from 0 to 1. So here's our entire set of real numbers. This is S, the entire set S right here. And the interval 1 minus epsilon, 1 plus epsilon contains this whole interval. So does 1 minus epsilon, 1 plus epsilon contain a point of S? Shoot. Yeah, so does this interval, 1 minus epsilon to 1 plus epsilon, contain a point of S other than P2 equals 1? This is our P2. And the answer is sure. Let's look at some of them. 1/2, 3/4, 1/4, 1/3, 2/3, etc., etc. So we can make up infinitely many points that are contained in this interval. 1 minus epsilon, 1 plus epsilon. Etc. So for a really big value of epsilon, the interval from 1 minus epsilon to 1 plus epsilon definitely contains elements of the set S other than the point P2 itself. Now let's look at another example with this same prospective limit point. And this time we'll let epsilon be very small. But we're still discussing P2 equals 1 as a candidate for limit point of this set. And now instead of looking at a really big value of epsilon, let's look at a little teeny value of epsilon. epsilon's very small. So this is 1 plus epsilon, and this is 1 minus epsilon. And this whole thing, this interval from 0 to 1, not including the endpoints, is our set S. So does this interval from 1 minus epsilon to 1 plus epsilon contain any points of S other than 1 itself? And the answer is yes. What about this point right here, halfway between 1 and 1 minus epsilon? That's going to be 1 minus epsilon over 2. And what about that point right there? 1 minus epsilon over 3. And maybe this point right here, 1 minus epsilon over 4, and so forth. So we'll note again, the interval 1 minus epsilon, 1 plus epsilon contains a point of S other than P2 equals 1. And we'll say, for example, one minus epsilon over 2, 1 minus epsilon over 3, 1 minus 2/3 epsilon, etc. You know what? If you're wondering about this, I think what I really meant to say was 3 epsilon over 4. But that's still it. So 1 is definitely a limit point of S. And we already found out that 0 is a limit point of S. Are there any other limit points of S? Well, we're going to find out. In the previous two cases, we looked at the endpoints of the interval, 0 and 1. 0 is not an element of S, but it is a limit point of S. 1 is not an element of S, but it is a limit point of S. So our first two limit points of the set S that we examined were not actually elements of the set S. Now we're going to look at a generic element of the set S. And I claim that X is also a limit point of S. Why? Well, we just go to the definition. And we'll look at epsilon really big. So here's the interval S from 0 to 1. And we'll put X right here. And let's say we have a really big epsilon. Here's our set S again. All the real numbers between 0 and 1, not including 0 and 1. And if I pick a big value of epsilon, then if I pick a big value of epsilon, then the interval from x minus epsilon to x plus epsilon contains perhaps the entire set S, the entire interval from 0 to 1. And so the interval x minus epsilon, x plus epsilon contains elements of S other than itself. And I'll say, see the picture. If S is if X is inside the set S, then somewhere between 0 and X, I can pick a point of S, and I'll call it S1, okay? That's a limit point. Over here, I'll pick a point S2, somewhere between X and 1. That's a limit point also. So between X and 0, I can pick another real number, S sub 1, that's going to be an element of the set S. Let's see, why can I do that? Well, between any two real numbers like 0 and X, there exists a rational number, there exists an irrational number. So I can take my pick. Between 0 and X, there's definitely a real number between them. I'll call it S1. And the interval from x minus epsilon to x plus epsilon contains this element of the set S other than X. And between these two real numbers, X and 1, there's a rational number. There's also an irrational number. I'll just pick one at random and I'll call it S sub 2. And this S sub 2, of course, is also in the interval from x minus epsilon to x plus epsilon. So S sub 2 is also a limit point of the set S. Now, those were pretty much easy pickings. Let's look at what happens when epsilon is small, just like we did in the other cases. Okay. We still have the same real number x in the set S, where S is the interval from 0 to 1, not including the endpoints. And now we let epsilon be a small number, maybe even a lot smaller than I'm showing it here. Now, does this interval from x minus epsilon to x plus epsilon contain a point of S other than X itself? Well, keep in mind, every point in the interval from 0 to 1 is already an element of the set S. So any element that I pick in here is going to be an element of the set S. For example, x plus epsilon over 2. And maybe this point right here, x minus epsilon over 2. Both of these points are in the interval x minus epsilon, x plus epsilon. And both of these points are in the interval from 0 to 1. So even in this case, the interval x minus epsilon, x plus epsilon contains a point of S other than example, x minus epsilon over 2, x plus epsilon over 2, x minus epsilon over 3, x plus epsilon over 3, and so forth. And you know what? I'm not done with this example yet. The first thing I'm going to do after I do some erasing is just write down the real numbers that we have established as actually being limit points of this set S, the open interval from 0 to 1. And then we'll look at some other special examples. Okay, let's summarize what we've done so far. We have a set of real numbers S, a non-empty set of real numbers S, where S is the set of real numbers in the open interval from 0 to 1. And we established that P1 equals 0 is a limit point of S. P2 equal 1 is a limit point of S. In other words, the end points of this interval are limit points of S. And we've also established that every real number that's contained in the set S is a limit point of S. So we can sort of restate this result by saying that all of the real numbers in the closed interval from 0 to 1 are limit points of S, where S is the open interval from 0 to 1. And I'm making a claim. There are no other limit points of S. In other words, all of the limit points of S that exist are limit points that we have already accounted for. There are no others. And here's how we'll show that there can't be any other limit points of S. The only candidates for limit point of S that we haven't already identified are going to have to be those real numbers that are outside of this closed interval from 0 to 1. Because we've already established that every real number in this interval is a limit point of S. So let's pick a real number outside of this interval. So the first case, maybe x is less than 0. Since x is less than 0, then 0 minus x is equal to epsilon. Or we could say 0 equals x plus epsilon. So let's draw that out. Here's the interval from 0 to 1. And over here someplace is x. And this distance is epsilon. And 0 is x plus epsilon. Now I'll shade in all of the real numbers that are part of S. The real numbers that are in the set S go from 0 to 1, not including the endpoints. 0 and 1. And I have a real number x which is outside of this interval. So you know what? Suppose I pick this interval, x plus epsilon over 2, and x minus epsilon over 2. This interval from x minus epsilon over 2 to x plus epsilon over 2 doesn't contain any elements of S. This interval is disjoint from the set S. So I'm going to note that the interval x minus epsilon over 2 and x plus epsilon over 2 does not contain an element of S other than X. So what does that tell us? The interval x minus epsilon over 2, x plus epsilon over 2 does not contain an element of S other than X. So X is not a limit point. X is not a limit point, LP of S. So any real number less than 0, any real number x less than 0 cannot be a limit point of S. Okay, let's look at our case 2. Okay, let's look at the other case. Suppose that x is not in the closed interval from 0 to 1, and x is not less than 0, so the only other possibility is that x is greater than 1. And if x is greater than 1, then x minus 1 is equal to some real number greater than 0 that we'll call epsilon. And we can rewrite this equation so that we have 1 equals x minus epsilon. Let's draw a picture of what that will look like. Here's the interval from 0 to 1. And here's x over here. And the distance between 1 and x is epsilon. I'm shading in the elements of S. The set of real numbers S is the set of real numbers between 0 and 1. And let's pull the same trick that I pulled before. Let's take epsilon over 2. And that will give us an open interval around x. From x minus epsilon over 2 to x plus epsilon over 2. And notice that the entire interval, x minus epsilon over 2 to x plus epsilon over 2, is completely disjoint from the set S. The set S contains no points of this interval, and this interval contains no points of the set S. So, I guess if x is greater than 1, x can't be a limit point either. Okay. This open interval contains no elements of S other than X itself. So X can't be a limit point. So if X is greater than 1, X is not a limit point. If X is less than 0, X is not a limit point. The only limit points that we have are the limit points between the only limit points that we have are those elements of the closed interval from 0 to 1. Now I think we want to look at some other examples. We've exhausted the open interval from 0 to 1. We're going to look at something else now. Here's a nice example. Let S be the entire set of rational numbers. I claim that every real number P is a limit point of S. In other words, every real number is a limit point of the set of rational numbers. Let's prove it, okay? We'll let epsilon greater than 0 be given. And we'll consider the interval P minus epsilon, P plus epsilon. And remember, very early back in Real Analysis 1, we had these wonderful theorems that we actually proved. Between any two real numbers, there's a rational number. And we also proved that between any two real numbers, there's an irrational number. Well, we're going to make wonderful use of those theorems right now. Yeah. Between any two distinct real numbers, for example, P and P plus epsilon, there exists a rational number, actually infinitely many of them. But there exists a rational number, and we'll call it Q. So what does that look like? Between P and P plus epsilon, there's a rational number that we'll call Q. Or put it another way, the interval from P minus epsilon to P plus epsilon contains an element of S, and remember what S is. S is the set of rational numbers. So it contains an element of S other than P itself. Let me look at that and make sure it makes sense. So hence, P is a limit point of S, where S is the set of rational numbers. And I'll make quick work of another example. Let S be the irrational numbers. Every real number is a limit point of the irrational numbers. And why would we say that? Why? Let epsilon greater than 0 be given. Between every two distinct real numbers, and for example, we'll say P and P plus epsilon. Between every two distinct real numbers, for example, P and P plus epsilon, there exists an irrational number. Oh, what should we call it? I'll call it Q again. And thus, the interval P minus epsilon, P plus epsilon contains an element of the irrationals an element of S, the irrationals, other than P. And that implies that P is a limit point of the irrational numbers. Well, that example and the one before it were sure a lot more interesting than working with the open interval from 0 to 1, weren't they? But they're all good examples. And now I think what I'm going to do is come up with an alternate characterization for the definition of limit point of a non-empty set S. You know what? I lied. I told you that right now I was going to do an alternate characterization of the definition of limit point of a non-empty set of real numbers, and I'm not going to do that just yet. There was one other example that I wanted to go through. We've seen some good examples. We need to see this example. So before we do the alternate characterization of a limit point of a set of real numbers, we want to see this example. Let S be the set of integers. Here's what I claim. I claim that the set of integers has no limit points whatsoever. None. And let's see, how can I do that? I think what I'll do is I'll look at two different cases. I'll first show that no integer can be a limit point of this set. So we'll pick an integer at random, our favorite integer, and we're going to show that that can't possibly be a limit point of the set of integers. And here's how we do it. Tell you what, instead of just writing out the proof, let me just draw a picture. Here's the integer x that we picked on the real number line. And here are the two closest integers to x plus 1 and x minus 1. In order for x to be a limit point of the set of integers, every interval of the form x minus epsilon, x plus epsilon has to contain an element of this set other than x itself. Can we create an open interval that contains x that contains no element of this set other than x itself? I think we can. We'll let epsilon equal 1/2. So here's our interval. Here's x minus epsilon. Here's x plus epsilon. That is x minus 1/2, x plus 1/2. And we observe the interval x minus epsilon, x plus epsilon contains no element of the integers s equals z other than x itself. So for all x and z, x is not a limit point. I'll let you look at that for just a second. So no integer can be a limit point of the set of integers. The only remaining candidates are those real numbers that are not integers. So let's take a look at one. If we look at our case 2, x is a real number that does not happen to be an integer, which means that there's some integer n such that x is between n and n plus 1. And we will let epsilon equal the minimum of x minus n and n plus 1 minus x. And I'll draw that out just so that we can see what it looks like. So here's x minus n, and here's n plus 1 minus x. But we're going to let epsilon be the smaller of these two values. This interval has to be contained in the interval from n to n plus 1. And just to show this, in this case, x minus n is the smaller of these two. So here's x minus epsilon, and here's x plus epsilon. I'm sorry, that's not right. This is epsilon, and this is epsilon also. N is equal to x minus epsilon, and this is just some point between x and n plus 1. But the fact of the matter is, this interval that contains x, this interval from x minus epsilon to x plus epsilon, doesn't contain the endpoints n or n plus 1. So this interval from x minus epsilon to x plus epsilon is contained in the open interval n to n plus 1. This interval doesn't contain n, it doesn't contain n plus 1 or any other integer. So this interval also contains no element of the integers. And this means, again, x is not a limit point of z. And that exhausts all of our cases. We showed that if x is an integer, x is not a limit point of the integers. And here we showed that if x is not an integer, then x is not a limit point of the set of integers. That accounts for all real numbers. No real number is a limit point of the set of integers. So the set of integers has no limit points. Now we can do that alternative characterization of the limit point of a non-empty set of real numbers. Okay, here's a big result of today's lecture. An alternate characterization of limit point of a non-empty set of real numbers S. A real number P is a limit point of a non-empty set of real numbers S if and only if for each epsilon greater than 0, the interval P minus epsilon, P plus epsilon contains infinitely many points of S. Not just one point of S, but infinitely many points of S. So let's see how we're going to do this. It's an if and only if proof, so we have to prove it both ways. And being the brave man that I am, I'm going to do the easy part first. So here's my hypothesis. And here's my conclusion. And like I said, being the fearless man that I am, I'm picking the easy part first. If for all epsilon, the interval P minus epsilon, P plus epsilon contains infinitely many points of S, then P is a limit point of S. So I'll say let the hypothesis be given. So we'll let epsilon greater than 0 be given. And we'll assume that the interval P minus epsilon, P plus epsilon contains infinitely many points of S. Now let's see, what am I trying to show? I'm trying to show that P is a limit point of S. Now, according to the definition of limit point of a non-empty set of real numbers, and by the way, we're assuming that S is non-empty. What it means for P to be a limit point of the set S is that P, for every epsilon greater than 0, the interval P minus epsilon, P plus epsilon, contains a point of S other than P. One point of it, only one point, at least one point of S other than P. Well, don't we already have that? This interval contains infinitely many points of S. Now, if this point contains infinitely many points of S, how many of those points can be equal to P? At most one, right? Which means that all of the other points, infinitely many of them, are not equal to P. So pick one. Pick one at random. So what did we just establish? For each epsilon greater than 0, the interval P minus epsilon, P plus epsilon contains a point of S other than P. And what does that mean? That means that P is a limit point of S. Okay. See, I told you I was brave. Yeah, I took the easy way out. Now is going to come the tough part. But I think with your help, I can do it. Okay, here's the converse, but I think we're up to it. Namely, if P is a limit point of S, then for each epsilon greater than 0, the interval P minus epsilon, P plus epsilon contains infinitely many points of S. Okay, let's have at it. I'll hit the chicken switch and say, let the hypotheses be given. That is, let epsilon greater than 0 be given. And suppose that P is a limit point of S. Okay. Now I'm still hitting the chicken switch. I'm going to take part of my hypothesis, that is, suppose that P is a limit point of S, and I'm going to write down what the consequence of this assumption is. Since P is a limit point of S, then the interval P minus epsilon, P plus epsilon has to contain an element of S other than P itself. So since P is a limit point of S, there's an element of S, little s1, where s1 is not the same as P, such that s1 is an element of this interval, P minus epsilon, P plus epsilon. And that's just the consequence of the definition of limit point as we know it. Now, how am I going to get infinitely many points of S in this interval? Well, here's what I'll do. I'll let epsilon of 1 equal the distance between P and S1. Picture-wise, here's P, P plus epsilon, P minus epsilon, and S is one of these points. It's either P plus epsilon of 1 or P minus epsilon of 1, where epsilon sub 1 is the distance between P and S. So this interval, P minus epsilon of 1, P plus epsilon of 1, is contained in the interval P minus epsilon, P plus epsilon. And that may be worth noting. Epsilon 1 is less than epsilon. Okay. Well, I feel pretty good about that. I think I might see a glimmer of light at the end of the tunnel. And before I erase too much more, let me modify the picture that I drew. S1, this is a point in the interval P minus epsilon, P plus epsilon, where S1 is not equal to P. And we're letting epsilon sub 1 equal the distance from P to S sub 1. So if we go a distance of epsilon sub 1 to the right and a distance of epsilon sub 1 to the left, we get the interval P minus epsilon of 1, P plus epsilon sub 1, and S sub 1 is one of those endpoints. So we'll note that epsilon sub 1 is less than epsilon. There's something else also to note. the point S sub 1 is not contained in the interval p minus epsilon sub 1 and p plus epsilon sub 1. This is an open interval, and S sub 1 is one of the endpoints. It's either the right endpoint or the left endpoint. So S sub 1 is not in this new interval. Now I guess I can continue. Since P is a limit point of S, there exists an element of S, we'll call it S sub 2, with S sub 2 not equal to P, such that S sub 2 is an element of P minus epsilon sub 1, P plus epsilon sub 1. See, we have a new open interval now. The open interval from P minus epsilon sub 1 to P plus epsilon sub 1. And this open interval has to contain an element of S other than P. And that element can't be S1 because S1 is not in the interval from P minus epsilon sub 1 to P plus epsilon sub 1. So there's some other element of S, we'll call it S sub 2, other than P itself, such that S2 is in this interval. Sounds good. I'm going to zoom in on what we have so far. Here's our limit point P, and here's the interval P minus epsilon to P plus epsilon. And this interval from P minus epsilon to P plus epsilon has to contain a point of S other than P itself. So we'll call that point S sub 1. And the distance from P to S sub 1 is epsilon. No, the distance from P to S sub 1 is P plus epsilon sub 1. So this distance is epsilon sub 1. And since since S1 is the end point of this interval, and this is an open interval, S1 is not contained in the interval from P minus epsilon sub 1 to P plus epsilon sub 1. But P is a limit point of S, so this interval, P minus epsilon 1 to P plus epsilon sub 1, has to contain a point of S other than P. And we're going to call that point S sub 2. So there's got to be some point S sub 2 here. And you'll never guess what we're going to do next. We're going to call the distance between S sub 2 and P, we're going to call that epsilon sub 2. So here's epsilon sub 2. And we go that distance in both directions. And this gives us P plus epsilon sub 2. And this gives us S sub 2, which is equal to P minus epsilon sub 2. So we got another open interval containing P. And this open interval does not contain S sub 2 because S sub 2 is one of the endpoints of this open interval. Now, before I go any farther, I just want to write down what we've established so far. Epsilon is greater than epsilon sub 1, and that's greater than epsilon sub 2. And the interval P2 minus epsilon 2, or rather the interval P minus epsilon 2, P plus epsilon sub 2, is contained in the interval P minus epsilon sub 1, P plus epsilon sub 1, and that's contained in the original interval P minus epsilon, P plus epsilon, and we'll also note that both S1 and S2 are contained in the original interval P minus epsilon, P plus epsilon. Let's carry this a little bit further now. Remember we made note a minute ago about this fact? Since S sub 2 is one of the endpoints of this interval, P minus epsilon, P minus epsilon sub 2, P plus epsilon sub 2. Since P is one of the endpoints of this open interval, since S2 is one of the endpoints of this open interval, S2 is not actually an element of this open interval from P minus epsilon over 2 to P plus epsilon over 2. But since P is a limit point of S, there has to be an element of S in this interval other than P itself. So since P is a limit point of S, there has to be some element of S, S sub 3, where S sub 3 is not equal to P, and such that S sub 3 is in this interval, P minus epsilon over 2, P plus epsilon over 2. So somewhere in this interval, from P minus epsilon over 2 to P plus epsilon over 2, there's this point S sub 3. And I'm going to put it right here. Here we go. Here's S sub 3. And of course, I'm going to call the distance from P to S sub 3. I'm going to call that epsilon sub 3. And look what we have. Oh, we have another open interval containing P. And since S3 is an endpoint of this interval, and what is it? This goes from S sub 3 plus epsilon over 3 and S sub 3 minus epsilon over 3. We have another interval containing P, and since S sub 3 is an endpoint of this open interval, S sub 3 is not in this interval. But since P is a limit point of set S, there has to be some element of S other than P in this interval, and we call that S sub 4. And right now, you're probably looking at what I'm doing saying, well, I see what's going on. how many more times do we have to do this anyway? Not many. As a matter of fact, maybe none. I'm going to bend down and pull out of my socks one of those magic phrases from math that simplifies things wonderfully. It's one of those phrases like without loss of generality. This is another one. Proceeding inductively. That we showed something was true for n equal 1. Then we showed it was true for n equal 2. Then we showed it was true for n equal 3, etc. And we keep on going, constructing things this way. And can we keep on going this way? Sure. We don't want to. We're all going to agree that we can keep on with S sub 4 and S sub 5 and S sub 6 and S sub 7. And here's the important point. The important point are these S values. S sub 1, S sub 2, S sub 3, S sub 4. All of these points are in the original interval from P minus epsilon to P plus epsilon. So I'm going to say, proceeding inductively, we create a sequence of points of S, namely S sub 1, S sub 2, S sub 3, S sub 4, so on and so forth. There's no end to what we can do here, such that S sub n is an element of P minus epsilon, P plus epsilon, for all natural numbers n. So let's see, what have we shown? Here's what we've shown. For all epsilon greater than 0, the interval P minus epsilon, P plus epsilon contains infinitely many elements of S. Namely, S1, S2, S3. Now, this was what we wanted to prove. For each epsilon greater than 0, the interval P minus epsilon, P plus epsilon contains infinitely many elements of S. But maybe I should just restate not just the destination that we wanted to arrive at, which I've done, but I want to restate something else also. Here's what we showed. We showed that if P is a limit point of S, then for each epsilon greater than 0, the interval P minus epsilon, P plus epsilon contains infinitely many points of S. And that's what we wanted to prove. So the alternate characterization of a limit point is that P is a limit point of S if and only if, for each epsilon greater than 0, the interval P minus epsilon, P plus epsilon contains infinitely many points of S. And we've got big plans for this theorem. Enjoy what we did today. In a couple more days, I'll put out another video.